All right, tonight we're actually going to take a jump back to Chapter 4, Section 4.4. I'm going to talk about what are called counting rules. Hopefully I'm getting any sound out of this one. All right, so here is the idea. Suppose we have 3 shirts, 4 pairs of pants, and 2 pairs of shoes. How many outfits do we have? And so we're going to talk about what's called the fundamental counting principle. The basic idea is as follows. So we had one of 3 shirts. So starting from a beginning point, we could go one of 3 ways depending on which shirt we picked. We had 4 pairs of pants. So then from each of these nodes, which represents one of the shirts we could pick, we can draw 4 branches to represent each of the pair of pants. This structure I'm drawing here is called a tree, and the lines are of course called branches. So far this tree has 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 leaves. They are in fact called leaves. But these aren't actually the ends of the tree, because from each of these leaves I can draw 2 branches to represent each of the 2 pairs of shoes. And so the end result is we have 3 times 4 times 2 equals 24 possible outfits. So what the fundamental counting principle says is that if you've got to make a bunch of choices, and you have k1 ways of making the first choice, k2 ways of making the second choice, k3 ways of making the third choice, all the way through kn ways of making the last choice, the total number of choices is simply k1 times k2 times k3 all the way times kn. You just multiply them together. And so this is pretty straightforward, but we can use this in some other contexts. So suppose I have 5 people whose names are A, B, C, D, and E, and I want to arrange them in a line. So how many ways can these letters be rearranged? And a rearrangement of a set is called a permutation. And so we can think of it this way. So from a starting point, you've got 5 choices for first letter, A, B, C, D, and E. Now, if you picked A first, you've now got 4 choices for your second letter, B, C, D, E. And in fact, no matter what letter comes first, you've got 4 choices for your second letter. Now, obviously, I'm not going to be able to draw this tree, but you can sort of see the reasoning now. If I took A, then I took B, I now only have 3 options left for the third choice. And then after I make the third choice, I've got 2 options left for the 4th choice, and then finally I have 1 option left for the 5th choice. Now it's hard to draw the whole tree out, obviously, because the tree is enormous, but we can use the fundamental counting principle anyway. The idea is you've got 5 choices for the first letter, and then no matter what letter you pick first, there will be 4 letters left for a second choice, and then there will be 3 letters left for a third choice. There will be 2 letters left for a 4th choice, and you've only got 1 letter left for the last choice. And this number is equal to 120. And this product, where you take 5 times 4 times 3 times 2 times 1, is referred to as 5 factorial. And 5 factorial means you multiply all of the positive integers between 1 and 5. So, for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is 720. 3 factorial is 3 times 2 times 1, which is 6. 1 factorial is simply 1, which is 1. And so these all count, these all count the number of permutations. Let's erase that and try that again. Of permutations. And if I want to write a formal definition, I'd say the number of permutations of n objects is n factorial, or n factorial is n times n minus 1 times n minus 2 times 3 times 2 times 1. And so this is the first sort of counting trick we have. Your calculator on your phone should have an exclamation point button that calculates factorials. But as you will quickly discover, these numbers get very large very quickly. So for example, 10 factorial, I'm just going to pause for a second. 10 factorial is equal to 3,628,800. And then 11 factorial is that times 11, and then 12 factorial is that times 12, and so forth. And this just gets very, very big very, very quickly. All right. Let's go back to A, B, C, D, and E. Except now I only want to pick 3 and put them in order. And so another way of putting this is I want a permutation of 3 things from a set of 5 things. And so we can figure this out using the fundamental counting principle. So if you want to pick 3 things from 5 things in order, then you've got 5 ways of picking the first thing, and then you've got 4 ways of picking the second thing, and you've got 3 ways of picking the third thing. And 5 times 4 times 3 is 60. And this number is called 5 permute 3, 5p3. So, for example, 7p2 is the number of ways of permuting of 2 things out of 7. And this is just going to equal 7 times 6, which is 42. So one way of thinking about this is that the first number tells you the first number of your product, and the second number tells you how many numbers will be in the product. But another way to think about this is that 7 times 6 is 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 5 times 4 times 3 times 2 times 1. And that seems like a convoluted way to do it, except that then you can see that this number is 7 factorial over 5 factorial, and that you can actually write that as 7 factorial over 7 minus 2 factorial. And so similarly, we can do the same thing with the original product we calculated. 5 permute 3 was 5 times 4 times 3, which was 5 factorial over 2 factorial, which is 5 factorial over 5 minus 3 factorial. And in fact, in general, NPK is equal to n factorial over n minus k factorial. So that is the number of ways of permuting k elements. But I have one more counting trick to do. And so in order to do that, I'm actually going to pick a smaller number, because 5p3 was 60. So what I want to do is I want to look at 5p2, which is 5 times 4, which is 20. So I can actually list all of those. You've got AB, AC, AD, AE. Then you've got BA, BC, BD, BE. You've got CA, CB, CD, CE. You've got DA, DB, DC, and DE. And lastly, you've got EA, EB, EC, ED. And so the important thing to understand here is that the order of the letters matter. So BA is not the same permutation as AB. But what if order doesn't matter? What if instead of having a first letter and a second letter, you just want to choose 2 of the 5 letters? And so, in fact, this is called 5 choose 2 and is written 5C2. So to understand what that is, notice so AB and BA, if the order doesn't matter, are the same. And AC and CA are the same, and AD and DA are the same, and AE and EA are the same. BC and CB are the same, CD and DC are the same, DE and ED are the same. So what happens is, if order doesn't matter, we can group the permutations in equivalent pairs. And then we get 5 times 4 over 2 equals 10, what are called combinations, instead of permutations. What happens in general? Well, let's look at 5p3 again. So if I've got 5p3, then you've got ABC, you have ABD, you have ABE, you've got a CB, you've got a CD, you've got a CE, you've got a DB, you've got a DC, you've got a DE, then you've got AEB, you have AEC, and you have AED. And so I'm going to write out the rest of these paused so you don't have to watch me do it because it's going to be really boring. Okay, where was I? BDE. Almost done. All right, so here's all 60 of them. And so the reason I wrote all 60 of them out is I want to show you something. If we don't care about the order of the letters, then ABC is the same string as BAC, is the same string as CAB, is the same string as ACB, is the same string as BCA, is the same string as CBA. And so what happens is each combination of 3 letters has 6 factorial repetitions. Not 6 factorial. 6 or 3 factorial repeats. That's crazy. And so the idea here is that we had here originally, if I erase a big blob in the middle, we originally had 5 factorial over 2 factorial permutations. But if I divide by 3 factorial, I'm going to get 5 factorial over 2 factorial times 3 factorial. And this number is called 5 choose 3 because it represents the number of combinations of 3 things. And notice here that 2 plus 3 is 5. And so the general formula is that the number of combinations, which is sometimes written n over r with parentheses, this is called n choose r, is equal to n factorial over n minus r factorial times r factorial. So, for example, 7 choose 2 would be 7 factorial over 2 factorial times 5 factorial. Or, if I want to stick to the order that I wrote the definition in, 5 factorial times 2 factorial, although again, multiplication commutes. So that doesn't matter. So this is the last of the 3 sort of counting rules that we want to know. So we're going to use these in class on Thursday to talk about a couple different probability distributions. So I hope this is helpful.